All right, let's get started. I know it's a little rough restarting your brain after spring break. I'm sure everybody was equally as depressed as I was to hear your alarm go off this morning. We got a few weeks left before we can officially check out here, all right? And so today we just got to keep going. We're going to start in on our next chapter on carboxylic acids and their derivatives. All right, so we're going to kind of lump together a bunch of functional groups together in this chapter, what we call our carboxylic acid derivatives. So first of all, we got our carboxylic acid carbonyl group, where that carbonyl carbon is bound to a hydroxyl group as well. All right, so this is our carboxylic acid. All right, and what we're going to see is this common theme here of our carboxylic acid derivatives, where bound to this carbonyl carbon is going to be some electronegative group, right? This is what's going to distinguish this set of functional groups from aldehydes and ketones, is we're going to be swapping out this hydroxyl group here for some other electronegative atom. All right, so get our carboxyl group going on here, carbonyl group rather. All right, we can also, instead of a hydroxyl group, we can put one of those very electronegative halogens on there. All right, and these are what are called acyl halides. This particular one would be an acyl chloride because there's a chlorine there. All right. Let's keep that an oxygen, but instead of a hydroxyl group, we're not going to have that oxygen bound to a hydrogen, but rather to some number of other carbons. This is what we would call an ester. All right, take our carbonyl carbon. Now it's going to be bound to a nitrogen. This is what we call an amide. Not an amine with a D, with an N, but an amide with a D. All right, and lastly, this one's going to look a little bit different than these other ones, but we kind of lump it together into this same group here, our nitriles. It turns out that that nitrile carbon having this high order bond to a more electronegative element behaves very similar to carbonyl carbons. So that's why we put nitriles into this same category. All right. And we're going to be talking about these functional groups. What we're going to see is we can easily convert some of these into other functional groups, but it's hard to go backwards, all right, to convert others. So anyways, these carboxylic acid derivative conversions is going to be a big topic of this chapter. But first things first, we're going to kind of start where we usually start with nomenclature. All right, and we're going to kind of go easiest to hardest here. First are carboxylic acids. Okay, so what we're going to see is we got a bunch of different functional groups, so we got a bunch of different functional group suffixes that we're going to be introducing. So step one, when we find that parent chain, we want that longest continuous set of carbons containing that functional group. And now we have this new functional group, our carboxylic acid. This gets this suffix, oic acid. And yes, we do actually have a space in our IUPAC name here. All right. So if we're going to go through and we're going to find our longest continuous set of carbons, we got these four here. So what prefix would we use? Number of carbons for bute. We got all single bonds, so butan-oic acid. All right, we would find and name any substituents, nothing new to add there. All right, we want to number that parent chain. All right, which way am I going to number? Left to right or right to left here? Right to left, right? So this is going to be carbon 1, 2, 3, 4. And what we want to note here is by the definition of a carboxylic acid, it has a double bond to one oxygen and another bond over here. So the only way you can have a carboxylic acid is if it's located at the end of a molecule on a terminal carbon. So it's always going to be on carbon 1. Do we bother building it into the name if it's always on carbon 1? No. So same logic that we saw with aldehydes. By the definition of what it means to be a carboxylic acid group, it has to go on a terminal carbon. So we just want to make note, we're going to have no locant in the name. All right, put it all together. So for carboxylic acids, really the only thing that we have to note here is we have our new ending for oic acid. All right, let's play this same game, but now we're going to do our acyl halides rather. All right, so I'm going to have another molecule here. I'll make this one a different size. All right, and again, what we're going to see is really we're only going to update our parent chain portion of our rules here. There's going to be nothing else new, really. We now have these new acyl halide functional groups. So we're going to use this suffix oil, and then whatever the specific halide is. All right, so if it were to be a fluorine, which you don't really see because they don't behave quite the same as all the other ones, but nonetheless, just to make this complete here, it would be an oil fluoride. If it was a chlorine, it would be an oil chloride. A bromine, an oil bromide. And an iodine would be an oil iodide. All right, so take a second and see if you can't name our example here. We got 5 carbons. All right, so this one would be pentanoyl bromide. All right, we don't have anything new to add to our substituents. All right, but what about when we number our parent chain here? Is there any way to have this acyl chloride group or acyl halide group in the middle of a molecule? No, same logic as before, right? You're necessarily going to have 3 bonds, so it has to be located at a terminal carbon. So again, we're just going to make notes, no locant in our name. All right, and then nothing new when we put it all together if we did have some substituents. All right, so same idea, we just have a new ending. We do have to tailor our ending to whatever our specific halogen is. 99% of the time, it's either going to be a chloride or a bromide. Nonetheless, we build that into our name. So we have this new OYL ending as well as our halogen name, pentanoyl bromide. All right, we're going to skip esters and amides for right now because they're kind of the more pain in the butt one. We're going to move on to nitriles. These ones are pretty easy too. All right, so first of all, when we draw our nitrile, let's be good. We want to make sure that we draw that geometry about that triple bond in that linear fashion. All right, we're going to show that sp hybridized carbon has that linear geometry. All right, and again, really all we have to update here is we have a new name for our parent chain. This new functional group, nitriles. They got really creative and they used the suffix nitrile. All right. Nothing new to add for our substituents column. Okay. When we number, we again are going to note, but by the definition here, that nitrile is going to have to be located on a terminal carbon. So no locant in the name. And then we got to assemble. All right, so everybody take a second. Attempt to name this one for me. All right, so first of all, one of the tricky things about these here is counting your carbons correctly. Most importantly, remembering that there is a carbon located at the base of that carbon-nitrogen triple bond. So we have 1, 2, 3, 4, 5, 6 carbons in my parent chain here. All right, again, everybody likes to forget this one right here at the base of that triple bond. So we have a 6-carbon parent chain. We're going to put this together with our new suffix nitrile. So we got hex, N-nitrile. And what's wrong with this here? We need the E, right? Same thing, we got this functional group suffix that starts with a consonant, so we're going to retain that E. So not hexanitrile, but hexane nitrile. All right, so we saw this with our thiols, one of those functional groups that start with consonants. We have to retain E because this thing here is a consonant. All right. Next up, we're going to do amides rather. Amides, they again got very creative using the suffix amide. All right, I will say you hear amide a lot as well, and I don't know which one's correct. I just pick one and stick with it. All right, so I call them amides. Sometimes you'll hear them pronounced with that long I, amide. All right, so parent chain, 3 carbons long here. We're going to use our new suffix, amide, amide, whatever. So this would be propan, amide. Prop for those 3 carbons, an for all single bonds, amide. All right, just like before, we necessarily have 3 bonds for this carboxylic acid derivative. So it's always going to be located at a terminal carbon, so we don't have to include the location of that in the name. All right. This was a particularly easy example of an amide here. Let's do another example. We'll keep these same 3 carbons to make a point here. All right, but nitrogen can have multiple bonds. So what if instead we had a secondary amide here where my nitrogen was bound to a methyl group, or rather there's a methyl group bound to my nitrogen. All right, so now we do want to make note in our substituents section here. Actually, I guess it would be more appropriate to put it in this section when we number here, okay? So first of all, if I number my parent chain, just like we always do, this would be carbon 1, 2, 3, but I have missed altogether this methyl group on my nitrogen here. All right, so this would be treated as a substituent, a normal methyl substituent. But how do we indicate that it's on that nitrogen? We're going to use locant of N. We're going to use N as a locant. So just like we would say there's a 2-methyl for a methyl group on carbon 2, instead we're going to say this is N-methyl propanamide rather. right? N-methylpropanamide for that methyl group located on that nitrogen. Cool, and then we, step 4, put it all together. All right, so amides, on the one hand, there's nothing really too crazy. We just have our new introduction of our new suffix that we use at the end. But we do have to note for secondary or tertiary amides, there could be alkyl groups on that nitrogen. We got to build those into our name as well, treating them as substituents and noting that they are located on the nitrogen. So we use that N as if it was a locant in our name. All right, and then lastly, these ones are kind of the biggest pain in the butt, are esters. Oops. And what makes esters a pain in the butt is that you've got these two halves to your ester. All right, there are two sets of alkyl chains here. This one over here and this one over here. Okay? So first of all, when we do our parent chain, which half are we going to pick? So that's a really good guess, is that we want to pick the longest one. And that's exactly what we did for ethers. But for esters, they're not two symmetric halves here. One of them is necessarily going to contain that carbonyl group, and the other one doesn't have our carbonyl group. All right, so our parent chain is always going to be the portion containing that carbonyl carbon. So our parent chain here must contain that carbonyl carbon. In this case, it is the longer one. Wouldn't matter if it was the shorter one. Whichever has that carbonyl carbon on it, that is your parent chain of your ester. All right, and so for that ester, we use this suffix -ate. All right, so everybody take a second and name my parent chain portion of this molecule here. All right, so my parent chain here is this 4-carbon butanoate. That's the parent chain fragment. All right. Now what we're missing is the other half of our molecule here. We're going to call this a special type of substituent, our ester substituent. And that is going to be a separate word that goes out front of that parent chain. Okay, and we're just going to name it as an alkyl group. All right, so for example here, this 2-carbon substituent, that would be an ethyl group, and that's just exactly what we're going to include in our name, but it's in a separate word that goes out front, so this would be ethyl space butanoate. All right, now in this particular one, it was a simple ethyl group here. If there were any branch points in there, we would have to name it as an alkyl group or a branched alkyl group. All right, and if it is a branched alkyl group, how do we number that ester substituent? Importantly, carbon 1 is always what's bound to that oxygen. All right, so we can just make note here, or branched alkyl group with C1 bound to that oxygen. I think it's actually bonded. I don't know. My brain's on spring break still. Anyways, whatever. You know what I mean. Cool. So what we're going to see is for our esters, our names have these 2 chunks to them, these 2 halves. All the information of our parent chain is in this parent chain portion of our name, and all that other bit, which we're going to call our ester substituent, is going to be in a word sitting out front. Cool. All right. And we number our parent chain the same way. That carbonyl carbon is necessarily carbon 1. And then we assemble it all together. We're just going to make note that we have these 2 halves. So all of that ester substituent information goes out front. And that first word. All that parent chain information in that second word. Cool. And so the last thing, and we're just going to do a bunch of examples here. The last thing that we're going to do, though, is we're going to go and we're going to update our priority list here. Remember, we've been keeping track of all these functional group priorities here. All right, now, truthfully, every single one of these has a priority. Every one of those different functional groups has a priority on this list here, so we could update this with all of them. But to be perfectly honest, it's kind of a huge pain in the ass dealing with them, especially when they're not the higher priority functional groups. So we're just going to make a note here that all of our carboxylic acid derivatives are higher priority than any other functional group that we've studied up until this point. All right? And we're not going to find a molecule that has a mixture of an amide and an ester or something like that. We're just going to note that if it's present with any of our other aldehyde, ketone, alcohol, thiol, alkene, or alkyne, that carboxylic acid derivative is going to win. That's going to be our highest priority functional group. Cool. All right, so let's just do a bunch of examples here. so let's start going through these. Okay, so I need my parent chain. My longest continuous set of carbons would be these 5 here. This would then just be a methyl group. All right, importantly, we learned of a lot of different functional groups here. This is what we call an acyl halide. All right. That carbon there, sorry. When we're going to number our parent chain, remember we're always going to start with that carbonyl carbon as carbon 1. So putting this together here, this would be 3-methyl pentanoyl chloride. All right, we got that methyl group located on carbon 3, our substituent. Our parent chain is that pentanoyl chloride. All right, now we have a mixture of 2 functional groups here. This is a ketone, and this one is a carboxylic acid. So which one's going to win in terms of priority? Carboxylic acid, right? All those carboxylic acid derivatives are greater than everything else. So here's our parent chain, our 8 carbons. We're going to number starting at that carboxylic acid carbonyl carbon. And because that ketone is our lower priority functional group, we don't consider it a functional group anymore. We've demoted it to a substituent or an oxo group. So this would be 3-oxo octanoic acid. All right. Now we got our amide here. Let me make some room. All right, my parent chain, importantly, is going to be the half that includes that carbonyl carbon. All right, so my parent chain here is going to be this propan amide. But we got all these other carbons we have to account for here. We have an ethyl group located on our nitrogen and a methyl group located on that nitrogen. We're going to treat these like normal substituents where we arrange everything together in our name in alphabetical order, but I'm going to indicate the location of them using that N as a locant. So putting everything in alphabetical order here, this would be N-ethyl, N-methyl, propanamide. Right? Just like as if they were located on carbons 1 and 2 or whatever it is, right? We build those in the name. We're going to do the same thing, but using that N as a locant. So N-ethyl, N-methyl, propanamide. All right, this one here is a nitrile. All right, how many carbons are in our nitrile here? 4, right? So we got 1, 2, 3. We don't want to forget that carbon at the base of our carbon-nitrogen triple bond. That is carbon 1 in my parent chain. So then this would just be a chloro substituent. All right, so 3-chloro bute for my 4 carbons, and for all single bonds, but then I'm going to retain that E at the end there, so 3-chlorobutane nitrile. All right, and then lastly, this one's a pain in the butt. I want y'all to try, just for the sake of time here, everybody take a second. Let's note here which fragment is going to be my parent chain and which one's going to be my ester substituent. Is the parent chain on the left or the right? Right, because it's got to contain that carbonyl carbon, right? So this half over here is going to be what contains all the information for my parent chain. This half over here is going to be for that ester substituent. Let me be good and include my lone pairs. Which means that you're going to have a bromo in that ester substituent portion of your name and a bromo in that parent chain portion of your name, right? Because of the location of these two bromo groups. Okay, so everybody just take a minute, see if you have not already, give this one a stab, and then we'll go through it. All right, so again, everything on this chunk here is going to be summarized in that second half of my name, my parent chain portion of my name here. And my carbonyl carbon is always carbon 1. So this is 3-bromo, that prop for my 3 carbons, propanoate. All right. But now I got to do my ester substituent. That's these 3 carbons over here. All right, so that would be a propyl group. And I have this bromo on there as well. We need to number our fragment here, our ester substituent. Again, carbon 1 is the one bonded to that oxygen atom. So I'm always going to start counting away from my parent chain here. So this would be 2-bromo-propyl space 3-bromo-propanoate. All right, again, all the information of that ester substituent built into that first word, all the information on that parent built into the second word here. All right, so 3-bromo-propyl, 3-bromo-propanoate. 2-bromo-propyl, 3-bromo-propanoate. Cool. All right, welcome back.